Hello, welcome back to Three-Phase Circuits. In this lesson, we're going to start the analysis of what we call the Y delta circuit, where the delta is at the load end. And specifically what we're going to do is do the analysis with this configuration of the load to derive the equation for the current shift that we've been talking about all this time. You probably won't have to do this kind of thing on an exam, but it does, we're trying to learn where things come from here. So you just file it away and you really understand where that comes from, and so then it gives you confidence in solving your problems, even though you probably won't have to actually derive this equation on an exam. But it's an easy derivation, so let's go ahead and do it. Where we're trying to go, I should say the goal, what we're trying to do is we're trying to prove to ourselves that this line current, AA, is actually equal to the square root of 3 times I capital A B, which we can also call, in most books you'll actually see it written as the phase current, right, I phi, with a phase shift of minus plus 30 degrees. All right, that's what we want to prove to be true because we're going to use it for every problem from here on out. So what we really want to do is we want to write some equations and figure out what is the relationship between these two variables. I mean, we've written it down, we know what the answer is, but ultimately we want to explore how is the line current related to the phase current? How are these voltages related to one another? So toward that goal, the very first thing we want to do is we want to write down, we want to take in our analysis the phase current IAB as the reference of 0 degrees, okay? And because we're taking that as a reference, in other words, this current here, we're going to call it 0 degrees. All the other currents in the circuit will just be measured relative to it. So if we take it to be 0 degrees, that just means that IAB is going to have some magnitude associated with it. We'll call it the phase current magnitude. It could be 3 amps or whatever. And it has a phase angle of 0 degrees. We're just doing this by definition because we're taking it to be the reference. If we adjust our oscilloscope and our timing properly, we'll get the IAB current to be exactly a cosine at time t0. Everything else is measured relative to it. So since this is a balanced three-phase circuit, and this is what we call the A-phase phase current, then if we take a positive phase sequence, let's talk about a positive phase sequence first. Positive phase sequence, right? Then that means IBC is going to be equal to what? It's going to be the same exact magnitude, but how is it going to be related to this? It's going to be negative 120 degrees shifted relative to it. And if you have a hard time remembering that, then you just go off to the side here. I guess I'll do it down here. This is going to be the A phase of whatever quantity we're talking about. This will be the B phase of whatever quantity we're talking about. And this will be the C phase of whatever quantity we're talking about. If it's a positive A, B, C sequence, then to go from here to here, it's a negative 120, and from here to here is a positive 120. Okay, so that's why for the B phase, we know we subtract 120 degrees because that's what it is to be a positive phase sequence. All right, now what would be that third phase? So CA is the third phase. You need to kind of get used to how these things are labeled. It's AB, that's the A phase, BC, that's the C phase, C has to go somewhere, back to A, that's what we call the C phase. It's going to be the exact same magnitude for a balanced three-phase circuit. What is going to be the phase angle relative to this? We're adding 120 degrees per our diagram here. So these are the three phase currents. We can write them down without any calculation because we know that it's a balanced three-phase circuit. Whatever this circuit is connected to, because it's balanced, that means that the magnitude of all three phases of these currents are going to be exactly the same. And if we take this one to be 0, again, if it's a balanced three-phase circuit, then they're going to all be separated by 120 degrees. Minus and plus because it's a positive phase sequence. If we were to redo this analysis for a negative phase sequence, the only thing that would be different is this would be positive and this would be negative because the B and C would be flipped around here. But for now, let's just keep it simple and say positive phase sequence only. These are going to be our phase currents that are circulating around this little triangle region inside the triangle. But these are different currents than the line currents which are coming in and feeding them from the transmission lines. Obviously they're different, that's why we're deriving this conversion relation to begin with. So how do we go from understanding what these currents kind of look like to figuring out what these currents, the line currents, look like? What we're going to do is we're going to go to this node up here. This is a node, right? Every place in a circuit, every node in a circuit obeys Kirchhoff's laws, always, right? So we're going to write a Kirchhoff current law at the A node, we're going to write an equation down. Later on, we'll do it for the B node and for the C node. Ultimately, we're just going to sum the currents in and leaving that A node. That's going to give us the relation between this current here and this current here. That's what we're trying to find. We're trying to find that relation. This is the logical place to look for it because the current's coming in and it's branching, so it's an equation that relates both of those variables. So let's go over here and we will write down, let's do it like this. We will take a Kirchhoff current loop at each node. So first, for now, let's just do it at the top node, I should say. So up here, what do we have? Remember, currents coming into a node are taken to be negative, and currents coming out of a node are taken to be positive. So here, this is a negative current. This is a negative current, CA. That's a negative current going to that node. That one's positive. So all we have to do is write that equation down. We have negative IAA, because that's coming in from the left, positive AB, because that one's coming out from that guy, and then we have negative CA, whoops, we'll call it ICA, because that's negative going into that node, and that's equal to 0. So that's just a Kirchhoff current law. And look, we have an equation that involves both of the variables that we care about. So let's solve this guy for IAA, the line current. IAA, all we do is move it to the other side, is going to be equal to IAB minus ICA. So what we have is an equation that expresses the line current in terms of not one, but two phase currents. Okay, two phase currents. But we don't know exactly what they are because we haven't drawn an actual circuit. But we actually know roughly what they are because down here we said for any balanced three-phase circuit, we know the AB phase is going to be some magnitude with some phase. We'll call it 0 for this as a reference. And the other one was CA. We know this guy is going to be the exact same magnitude at positive 120 phase. So we're going to take these two currents and we're just going to stick them into this equation right here. So what you're going to find is that IAA, the line current, is equal to AB. That one was whatever the number is, we're calling it I phi, 0 degrees, minus, what is this one? It's exactly the same magnitude, and it's positive 120 degrees. Okay, so at this point, when you get to the analysis, you might be stuck, okay? If you remember back when I derived the voltage shift relationship in the previous set of lessons for the YY circuit, we went through an extensive amount of math to get to the final result. But at the end of the day, after I did all of that math and I did it exactly, right, I kind of showed you how you could just sort of prove it to yourself in a calculator, right? And so we kind of just went with that from then on because I'm not really trying to make you all mathematicians. I'm just trying to show you where this stuff comes from so that you know logically it follows from something that you can understand. If you were to do this exactly without any calculator shortcuts or anything, you don't know what this phase, what this actual magnitude is. It can be anything. Whatever the phase current is in the circuit circulating around that triangle, it's a number here in front of the phasor. But if you wanted to figure out what this relation really was, here's how you would do it. You can't really subtract these phasors in magnitude phase form very easily. What you would have to do is convert this to rectangular notation. It would be, you had to convert a polar number to real part plus imaginary. You would do that, you would have a variable in there, but that's what you would do. You would convert this. You would have a cosine and a sine of 120 in this term, and you have a cosine of 0 and a sine of 0 in that term. You would get it as real plus imaginary for this term. You would get this real plus imaginary for that term. Then you would add the real parts and you add the imaginary parts. The reason you broke it into real and imaginary to begin with is so you can add the real parts and add the imaginary parts. You can't add them easily in this form. But once you add them and you get a final real part and a final imaginary part, you convert that back to a polar representation. How do you do that? You know how to convert rectangular back to polar. You use the Pythagorean theorem of the real and imaginary part to get the magnitude of your phasor, and then you use the tangent that defines the angle. So there's some math involved, but ultimately what you're going to get is you're going to get a final relation, and when you do all the math there, you're going to get this. You're going to find that the angle that you get when you do all that inverse tangent stuff, you're going to get 30 degrees in there, and you're going to find a square root of 3 that's going to arise from that Pythagorean theorem when you go backwards from Cartesian to polar representation. I've done this kind of work in the last section, not in the last section, but in the last batch of lessons for YY circuits when we were doing the voltage relation. And it's a little bit, it's not hairy, it's just a little bit of a digression. We don't need to really do it so much because you can convince yourself that this is all, that it's true by doing the following thing. What you can do is you can, instead of doing it exactly, just pretend that your phase angle is, or that your phase magnitude of the current is 1 amp. So what you would have is 1 amp at an angle of 0 degrees minus 1 amp at an angle of 120 degrees, right? The reason I'm sticking a number in here is so that you can put it in your calculator. And when you put this in your calculator, what you're going to get is square root of 3 at an angle of negative 30 degrees. So what you found is that the line current, if the phase current was actually fixed at 1 amp, right, and we know the angles because it's a balanced circuit, then if you stick 1 amp into this relation, the line current is just going to be square root of 3 times, with a phase shift of negative 30 degrees. Negative relative to what? Negative relative to our phase anchor here, our reference of 0, okay? So in other words, you should be able to convince yourself from this that the general form of the equation, if we don't fix this at 1 amp, is just going to be equal to exactly what we said it would be equal to. Square root of 3 times whatever this magnitude actually is, phase shifted. In this case, for a positive phase sequence, it was negative 30 degrees. But that's because it was a positive phase sequence. If we redo this analysis again, you would have a plus on the bottom. Now let me kind of save that for the end. Let's just leave this for now for the positive phase sequence. So again, this is exactly what we get with the calculator. It's just because we put a 1 here, then this 1 is right in the middle there. But if you relax this and do the analysis completely, then what you'll find out is it's square root of 3 times whatever the magnitude of these currents are, and then phase shifted the same way. Okay, so that's important. Basically, you found out what the relation actually is. Now let's go for the other phases. How would we do the same thing for we did the thing for phase A by just writing a Kirchhoff current law there. What would happen if we wrote a Kirchhoff current law at the B phase and then again at the C phase? What you're going to find is for the B phase, you would write the current here, the current here, the current here, and you would find a similar relation. Let's go ahead and show ourselves that that's the case for the B phase, or I should say at the B node. Okay, at the B node, and I'm going to do this a little fast because ultimately it's the same thing. What you're going to find is that IBB is equal to IBC minus IAB. It's a very similar equation to what we have right here. We have I, little b, big B, is equal to IBC minus IAB. Convince yourself that's true because ultimately, if I were to move BB to the other side, it would be negative, just like this one. And then and you have a subtraction of 2 other ones, which is what we have here. So this is what happens when we move it to the other side. Basically, this line right here. This is exact mirror image with just different phases in there. Now, BC and AB, we need to stick in there. BC had an angle of negative 120, and AB had an angle of 0. So the way you would do that is you'd say BB, okay? BC would be I phi angle negative 120 minus AB I phi angle 0. All right? And again, if you were going to do this exactly, what you would do is you would convert this to a Cartesian representation. You'd have this times the cosine of this, that'd be the real part. This times the sine of this, that'd be the imaginary part. This times the cosine of this, you'd have the real part. This times the sine of this, you'd have the imaginary part. Then you'd add the real and imaginary parts, taking the cosines and the sines as numeric values. And then you'd have a Cartesian, real imaginary representation of the answer for this. But then you'd convert back to polar because we like to work in phasors. And to do that, you have Pythagorean theorem of real and imaginary part and inverse tangent to get the angle. You do all of that, what you're going to end up with is IBB is equal to square root of 3 times I phi, in the general case, I phi, and then you have the angle of negative 150 degrees. Okay? So what this is saying is that for the B phase, for BB, the B line current is going to be equal to square root of 3 times whatever the phase current is for the B phase, which is the same for all of the phases, and you're going to shift that negative 150. Okay, relative to what you its phase current. Okay, But look at what its phase current was. For the B phase, the phase current was already negative 120, so to make it negative 150, we subtracted 30 degrees again. So you see the base rule is the same. We subtract 30 degrees when we're going from the phase current, which is what we have, and we're trying to find the line current, we're always subtracting 30 degrees. Okay, we just started at negative 120, we subtract 30, and we get to negative 150. I promise I'll summarize this a little better at the end. Let me just kind of get through them all. Now let's go to the C node. What happens at the C node? You have current coming in, current coming out, and then over here you have line current. I haven't drawn it, but you have line current coming in also. So what you would have is ICC, that's the line current, is ICA minus IBC. So this line current is going to be equal to the line current in the same direction minus the BC like this. Now we know what CA and BC are. CA is this one, and BC is this one. So you have the 120s in there. So ICC is equal to CA, phase magnitude, angle 120, minus phase magnitude of the current, negative 120. So again, same thing. You can do it exact, or you can stick it in your calculator, putting a 1 in here and a 1 in here. So 1 angle 120, 1 angle negative 120, subtract them, and then you should be able to convince yourself that ICC, IC big C, is the square root of 3 times I phi at an angle of 90 degrees. And you say, wait a minute, that's not 30 degrees. But you got to remember what it is. You're taking that phase current and then you have a 90 degrees here. But what is that phase current for the C phase? You started at 120 degrees. So if you subtract 30 from that, you're going to get 90 at the end, right? So to summarize all of this stuff together, what you get is you'll have IAA is equal to square root of 3 I phi negative 30. That's for the A phase. BB square root 3 I phi negative 150 degrees. And ICC square root of 3 phi 90 degrees. Okay? So what you're basically finding is that whatever you start with for your phase current, you subtract 30 degrees to get the line current. If for the A phase, you start at 0 degrees, if you subtract 30 degrees, you get negative 30 degrees. For the B phase, if the phase current is already at negative 120, you subtract 30 degrees, you get negative 150. For the C phase, you already start at positive 120, you subtract 30 degrees, you get 90 degrees. So this leads you to the following summary, which is what we already know, that, let's write it for the A phase, AA is equal to square root of 3 I phi, and we have an angle because we're subtracting negative 30 degrees every time. For a positive phase sequence, it's going to be negative 30, we're shifting by, okay? And then I want to show you for a negative phase sequence. See, this was all done for a positive phase sequence. What changes for the negative phase sequence? All of these Kirchhoff laws that we wrote, they're all based on the diagram. So the equations actually don't change because the reference directions are fine and the node Kirchhoff current laws are all the same. But if it changes to a negative sequence, this becomes C and this becomes B, which basically means this becomes positive 120 because this would now be B up here, positive 120, and this becomes negative 120. So what you end up having is negative 120, positive 120. So you see for every one of these, I'm not going to go back and do them all again, but if you change it to a negative phase sequence, some of these angles are going to end up being negative of what they are in our initial calculation. If you stick them back in your calculator with negative angles, you're going to get a different shift here. So what would you get if we redid all that really quickly and I didn't bore you to death with it? What you would get for a negative phase sequence, I'm going to write it over here, negative phase sequence, because I don't want you to confuse it with the positive phase sequence. What you would get is IAA is square root of 3 I phi, and you would have a shift of, what do you think, positive 30. If you went back and just stuck the different phase sequence back into our equations and got the thing again, you would have positive 30. And then for the B phase, you'd have square root of 3 I phi. What would you have here? Instead of the negative 150, you'd actually end up with the positive 150. And then if you had this, square root of 3 I phi, what would you get for the C phase? Instead of 90, you would actually get negative 90 degrees. Why? Because if it were a negative phase sequence, nothing changes with the A phase as far as this original angle of the phase current. So we're saying ultimately that kind of by assimilating all of this down into one equation, if it's a negative phase sequence, you choose a positive phase shift of 30 degrees. So if you start here at 0 for this phase current, you add 30 degrees to it, this is what you would get if it were a negative phase sequence. If you started with this for the B phase and you add 30 degrees to this, if it were a negative phase sequence, you add 30, you would get, actually, this would be a positive. If it were negative phase sequence, I almost screwed up. If it were negative phase sequence, this would be positive 120, right? It would be flipped. Positive 120, you add 30, you would get positive 150. And if this were a negative phase sequence, this would be negative 120, you would add 30, and you would get the negative 90. So the bottom line is that whether or not it's a positive or a negative phase sequence, this is the granddaddy equation that governs all of it. I've written it in terms of, you know, I phi here, but you can also write it in terms of, you know, you see that a lot in books, but I usually like to write it like that because I like to write a single equation for the A phase. So if you were going to read this equation for the A phase, the way you would read it is you would say the line current is going to be equal to the phase current for that phase times the square root of 3, meaning increase the magnitude. But if it were a positive phase sequence, you would choose the top sign and you would subtract 30 degrees from that phase. No matter what phase you're working with, you stick it in here and you subtract 30 degrees. Well, I've shown you that over and over again, and you end up getting these numbers. And it holds true for any phases that you have. That's what you're going to get. And then if it were a negative phase sequence, you just choose the bottom sign. Now, the way that we're going, which means you're going to be adding 30 degrees. And the way this is going to go down for all of our problems is going to be similar to what we did for the YY circuits. We're going to be given a circuit or a bunch of words to construct the circuit. Then we're going to write a single phase equivalent circuit. And that's usually going to allow us to find the line current or some other quantity, right? So we'll usually actually have the line current, this guy. And then we might have to find the phase current. So we'll have to divide, and we'll have to divide, and we'll have to keep track of our signs accordingly. But this is going to be the equation that governs it. So when you start your problem, you immediately have to identify what phase sequence is it. That's going to be a positive phase sequence. You're going to choose the negative sign, and the negative phase sequence, you'll choose the positive sign. That locks that down. And then for the rest of the calculations, you find the values associated with the A phase. So for instance, we might find this for the A phase and we find this for the A phase. Just like for the voltage problems, once we have the quantities for the A phase, we can find the B and the C. We don't have to do this equation again and again for the B and C phase. I've shown you that you can do that and you get the same answers, but you don't have to do that again and again and again, because once you have the A phase, you just subtract 120 and add 120 to get the B and C phases. In fact, you can see this right here. This is a positive phase sequence in purple, right? If we found this stuff for the A phase, this is what we'd be shifting by negative 30. But to find the B phase, we minus 120, boom, that gives you that. And we add 120, boom, that gives you that. If you were to start with this in the negative phase sequence and you calculate this guy for the A phase, then to get this, don't forget, you add, because everything's flipped around for the negative phase sequence, you would add 120, subtract 120 to get these. So this granddaddy equation applies to every phase of that triangle, relating the current coming in from the line, where's it at? The current coming in from the line to its corresponding phase current. The current coming into the line for the B phase to its corresponding phase current. The current coming in from the C phase to its corresponding C phase current. That's what it relates. So you can apply this equation to every phase individually. However, in practice, what we do is we find the quantities for the A phase, line current, phase current, and then we just add, subtract 120 to get the others, just like we've done for the voltage problems in the past. That's all I want to say. It's a lot of words, but understanding that is critical to doing well in these problems, because now I can just show you a problem and we'll just be able to crank through and solve it. So let's go and do our first one in the next lesson right now.